This is a lecture from Open Tuition. To benefit from the lecture, you should download the free lecture notes from opentuition.com.
We've already dealt with sensitivity analysis, where you can be asked to calculate expected values, where you can be asked to calculate, and Monte Carlo simulation, where it's just being aware of the idea. There are two last things, both of which very quick. The first is standard deviation. And it's very easy here, but to explain the relevance of it, think back to expected values. Suppose I had a flow which was either, we estimated was going to be 12,000 or 8,000 with probabilities 0.5. Well, whenever we're uncertain, there's two outcomes and we've got the probabilities, we base it on the expected value, the average is 10,000. Suppose you were faced with another choice, perhaps those were MPVs for a machine, the expected is 10,000. But there was another choice available, which may give 15 or 5. Again, with probabilities 0.5. Oh, it gives exactly the same expected value. And so you'd say, oh, well, I don't care which we do. But something that would affect you, of course, is the first one might give you 12, it might give you 8. A bit more than 10 or a bit less than 10. The second one, is surely a lot riskier. And that although the average is 10, it might actually give a lot more or a lot less. And that's really the nature of risk, as to how much it might be higher or lower. And so anyway, it may influence you in real life as to which is better, not just what the average return is, but how much it's likely to be higher or lower than the average. Well, standard deviation is a standard way of measuring the extent to which it's higher or lower. And so you just could be asked to work out a standard deviation. It's very easy. It wouldn't be to any great level. Look at exercise 3. There's a formula above, but it's silly just to stare at a formula. Let me explain with example 3. It says we're going to get a return of 10%, 15% or 20%. These happen to be percentages. It could be dollars, it could be like I had a minute ago. Return of $15,000 above. Doesn't matter. We know the probabilities of each outcome. 0.2, 0.5, 0.3. And so the expected or the average multiplied by the probabilities and add up to 7.5, 6 comes to what? 15.5. There is the expected or the average or the mean. Mean is another word for average. Now that should be automatic, absolutely no problem, because I'm going to explain, if you like, the formula for standard deviation. I'll give these symbols. I'm going to call the return x, the probability p, and the standard symbol for the average or the mean is x bar, x with a bar on the top. Anyway, that's the mean, but as I said before, about a bit of introduction, we want some measure of how much the spread is, how much higher or lower it might be from the 15.5. So we know it's actually going to be 10, 15 or 20. Let's measure the deviation, the difference, how far away it might be from the average. So x minus x bar, if the return is 10, 10 away from 15.5, it's minus 5.5 from the average. 15 as against 15.5 is minus 0.5. 20 is plus 4.5. And so there's the difference in the average. And how about the average difference? Well, the only problem is, if you took the average of those, if you multiply by the probabilities, I'm not going to do it, because some are below, some are above, you'd actually end up getting 0, if you think about it, or try it if you want, which would be a bit meaningless. So what we do, to avoid the sign problem, we square those differences. And if you square them, a minus times a minus becomes a plus. So they all become positive. And then we take a weighted average, we multiply by the probability and add up. So in each case, square the difference, multiply by the probability, and again add them up to get the average. So let's do it. 5.5 squared times probability 0.2 is 6.05. There we go. 6.05. 0.5 squared times the probability 0.5 is 0.125. And finally, 4.5 squared times the probability 0.3 is 6.075. Add them up, 6.05 plus 0.125 plus 6.075. They're all positive because we'd squared. Comes to 12.25. Now that 12.25 itself is a measure of spread, because the bigger they differ from the 15.5, the bigger that figure would be. The only problem is, those differences here were in percents. We've squared them and taken the average, so these are like 12.25 squared percents. That doesn't really mean anything. Or if, I say, it doesn't matter what units they are, if these had been dollars, the differences would have been in dollars. But because we then squared them, you'd have got squared dollars. So to get back to the same units, the standard deviation is the square root of that figure, which is 3.5. And we're now back to the same units. So because it was percents that went in, this is a percent. Had the original figures been dollars, this would have been dollars. So that should now make sense of the formula that's immediately above the example. In general terms, what did we do? We took the differences from the mean, x minus x bar. We squared them and multiplied by the probabilities. We added them up, which is what sigma means. And then we took the square root. So the formula makes it look rather more complicated than it actually is. You'll see the question does ask also for coefficient of variation. All this is, remember, that 3.5, here percents, it could be in dollars, but it is a measure of the spread, how much higher and low it might be. But is that a lot or is it a little? You know, what I'm getting at is if the returns themselves were sort of 80%, 90%, 100%, 3.5 isn't very big. That's a fairly small amount. On the other hand, if the returns themselves are 1%, 2%, 3%, 3.5 is huge. And so, to give it some relevance, the coefficient of variation you can see there, you're given the form, it's a standard deviation divided by the mean. Standard deviation 3.5%, the mean 15.5%. And so what does that come to? 0.226, sorry, if you want 22.6%. So it gives you just an indication of how big is big. If this was 80%, good heavens, there are huge ups and downs. If this was 2%, very tiny ups and downs. It just makes it a more relevant, relative figure.